Hi, I'm Scott Urschel with Pylon Aviation. We're the distributor for Airbus helicopters for the US and Canada. This is our aerobatic BO-105 helicopter. This is a current standard category aircraft that we put into experimental so we could allow us to do aerobatic maneuvers. The helicopter is unmodified. The only reason why it's an experimental is because the flight manual prohibits aerobatics. It was certified to plus 3.4 Gs -1. Most of our routine that you saw the last couple days was probably in the 2.8 to 2.9 G positive and about a half a G negative. This aircraft is manufactured in Germany. It was built by Messerschmitt Bocal originally, which became Eurocopter and then Airbus. Airbus owns the type certificate for the helicopter. Currently about 1,400 of these were manufactured. About 400 or plus or minus are operated worldwide still to this day. The rotor hub on this is the unique piece of it. It's a bearingless, hingeless rotor system, or referred to as a rigid rotor system. The rotor hub is manufactured out of a forged piece of titanium. Rotor blades are fully composite. There's no lead lag or flapping hinges. That's all happens within the rotor system. It's the rotor blades themselves. We'll, on our pre-flight, first thing we do is make sure we have our battery plugged in. We normally unplug it when the aircraft's been sitting for a period of time, and come back in here, and I'll open this up and you can look into the just do a quick systems check here. This aircraft has a mast moment indicator. The mast moment indicator shows the bending moment of the mast. We do a test on this, so we'll test it to see that it goes to 100%, and then it'll come back down to 0. It shows here that we don't have an exceedance, so we never had an exceedance unless the light is on after we do the test. There's a strain gauge in the mast because of the rigid rotor. On the ground, if we move the cyclic stick, we can actually put a heavy bending moment into the mast, and we monitor that. A lot of people ask me, how do I do aerobatics and not exceed mast moment loads? Well, the fuselage will follow the mast around as we do these different maneuvers. So my mast moment indicator hardly moves when I'm in normal flight, and then in aerobatic flight it'll stay well out of the amber region. We'll do a warning light test, check our fire test lights. We have fire monitoring for both engines. This uses C20B Allison Rolls-Royce engines, 2 of them. We have TOT gauges, torque gauges. We're just making sure that everything is approximately 24C today. All of our temperatures are down. We have a header tank, so the main tank transfers fuel into the header tank, and this allows us to do these aerobatic maneuvers without losing fuel pressure to the engine. We cannot sustain very long inverted flight due to the oiling system of the engines, so we're really limited by oil pressure, but none of our limitations are exceeded during any of the maneuvers you see today. We'll do a couple quick checks here. We'll do igniter check, both engines. We can hear the igniters running. Listen to those. And make sure our fuel transfer switch is off. We have an AUX fuel tank in the aircraft. We'll show you that in just a minute. And come back down. All right, so our fuel system, our oil system, I'm sorry, our oil tank for engine number 2, which is the pilot side, and engine number 1, which is the co-pilot side. Over here we have 2 oil filters. These are facet oil filters, and on the bottom of these we have a bypass indicator, and we can feel that that is still in the filter system, which means that the filters have not bypassed. And then we have another one over here on the side for the transmission filter, sits right back up in there. And then this is our hydraulic fluid for our rotor brake. One thing you won't be able to see is the transmission level is back in here, and we can see that that is at the normal level, and that our caps are secured on the aircraft. So we come up here, we check that all of our PC links are safety wired and that they're free moving. So we have safety wire locking up here and safety wire on the bottom. Cotter pins on all the castellated nuts. This is the rotor tack. This is a special system that we run. We have a full data acquisition system in the aircraft with 32 channels of data. This is monitoring the rotor RPM. We have cotter pins here on the bottom of the main blade bolts along with safety wire. These are vibration absorbers, and in flight they sit out parallel to the blade, and then they move up and down as the blade flaps, and we come in and out of effective translational lift. These are primarily used to dampen that vibration, but in flight they really serve no purpose other than dampening the rotor system's vibrations. So as we bring the blade around, we check to make sure that these are free as well. PC links are free, safety wired, cotter pinned. Looking for all of our safety wire. This rotor head actually has a Mobile Jet 254 in it, and you can see there's two lines up here, a full line and a min line, and this is actually running in an oil bath, and this allows the blades to pitch for collective pitch control. These are our main blade bolts. There's studs in the rotor hub, and then these are all safety wired. That holds the rotor head on. Very important part. Our normal inspection procedures are, there's a 50-hour, 100-hour, and 150-hour, and then inspections that are calendar requirements of 12-month, 24-month, 36-month. There's a 6-year inspection. Typically, every 10 hours, we open all the cowlings, pull the cowlings all off the aircraft, just based on what we do. We want to make sure that everything's perfect. We have never found anything abnormal from normal operating procedure that we have. So we've been very fortunate. Maintenance is twin engine helicopters are expensive to run, and there are normal everyday leaks and minor squawks that we have, but nothing that's been related to aerobatic maneuvers. So this is the C-20B Allison Rolls-Royce engine. This is used in the Bell Jet Ranger, the Hughes 500, the Enstrom as well. It's a gas turbine. It's 425 horsepower, starter generator. We're just checking the cotter pins here on the motor mounts. The highest loads you have on the engine compartment are the gyroscopic forces when we're doing rolls and loops, because the engine's turning at very, very high RPM, and consequently those gyroscopic loads are very, very hard on the motor mounts. So during some of our inspections, when we pull the engine out, we NDT the motor mounts just to make sure we don't have any cracks. We've never found any real problems with that, but it is something that we take a close look at. And here we're just primarily looking for torque stripes on our fuel control governors, just to see that we don't have any broken lines or B-nuts that are coming loose. Yep, not a whole lot we ever have problems with it from an engine perspective at all. Make sure that all of our exhaust stacks are secure, so nothing goes through the rotor system. If you notice, all of the latches and the Zeus fasteners are captivated in these spring tabs, so that if we do have a Zeus come loose in flight, it doesn't fly back and go through the rotor system or the tail rotor. Normally we have our smoke system here, so the smoke generators fit into these brackets right here and are captivated, and then there's a wire with electric matches that come up and light the smoke system off. So you can see on the back here we have a little quick release device, and we snap these open, put the ground and the positive into here, and then I have a sequencer and an arm switch to light the smoke. This air dam right here, we check to make sure that this is secure. This is actually to prevent the aerodynamic effect of the airflow to come around the back of the cowling, and it would blank out the horizontal stabilizer. So early in flight test, Messerschmitt found out that they were getting unusual handling characteristics. So this it looks like a high drag device, but it causes less drag than the disturbed airflow over the horizontal stabilizer. So as the airflow comes up here, it disturbs this, and then now we get clean air across the horizontal stabilizer. The tail boom, unlike most helicopters, is not a monocoque structure. There are actually longerons in here that go the full length of the tail boom all around the inside of the tail boom into the structure of the aircraft. There's a lot of titanium in this machine, in the engine compartments, in the firewalls. We have firewall separators between both engines so that if we were to have a catastrophic failure of one engine, we don't take out the other one. I've never had an engine failure in this, but it flies pretty good on one engine at the weights that we fly. Typically, our single engine weights that we're at right now, we could fly away from a normal takeoff, or if we were in flight doing our routine, we could easily land the helicopter if we had an engine failure. Horizontal stabilizer, as you can see, is very high structure. We have these high yield bolts in here to hold the horizontal on. The vertical fins actually are rubber mounted, and that's due to the vibration to help dampen that so we don't put a lot of load in the horizontal. We of course have our GoPro mount here. When we bring the hardware, we actually would have GoPro for you. You'll see some of that in the video later, I'm sure. We have a 42-degree gearbox and a 90-degree gearbox here. On this gearbox, on this side you can see the oil level. Typically these shouldn't change. The hub on the rotor system up here is all titanium, like the main rotor hub. And on the back of the 90-degree gearbox, as you look up there, you can see the fuel oil level. And once again, composite tail rotor blades with titanium leading edge abrasion strips. The flight control system on this aircraft to the anti-torque pedals, or the tail rotor, is mechanical. There's no boost or servos in there whatsoever. So you have a mechanical push-pull tube to the anti-torque pedals, but the rotor system has a dual hydraulic system, and we'll be pre-flighting that here shortly. So we're checking to make sure the horizontal's solid, our tail stinger's not loose, none of the hardware's loose into here, castellated nuts, no damage on the tail boom, no loose rivets. In here, it's our baggage compartment, and this is our AUGS fuel tank. This is a 50-gallon AUGS fuel tank. We just typically use this to ferry the aircraft across country. It burns about 1 gallon a minute of jet fuel, so it's a little thirsty. For our aerobatic displays, we typically run no more than 40 gallons of main fuel to keep the weight down. So number 2 engine over here. It's our governor. On the other side, you can see the fuel control. Again, we're looking to make sure all of our B-nuts, all of our torque stripes are good. Motor mount cotter pins are in. Part of our data acquisition system, you can see it on this side much better. This is a pressure transducer that's measuring torque indication that goes to the gauge. We have 2 of these, one for each engine, and it feeds into our data acquisition system, and it monitors the torque of each engine. So when I go back, and you'll see a video later of my display, I practice with this data acquisition system, and I can look at torque, temperature, altitude, airspeed, rotor RPM, flight control position, and it all syncs to my video system through a special CAN bus. This data is very important because as the helicopter is inverted, we change the load on the rotor system. So the torque actually goes up as opposed to going down. And a lot of the physics behind flying this are not aerodynamic as much as they are the gyroscopic forces are very prevalent with this size of rotor system, because most of our maneuvers can be done from a hover. So we don't have any aerodynamic forces per se other than on the rotor system. As you can see, it's difficult to see a lot in here, so that's why every 10 hours or so, or several aerobatic flights, we'll pull all these cowlings off, and then we have 100% access to the engine, and our mechanics or myself will go through and do a much more extensive pre-flight. So this is the most critical system in this aircraft, is the tandem hydraulic unit. It's actually quite an impressive system. Most hydraulic systems are open loop. They have a reservoir that gravity feeds into the system. This is a pressure system. So we have two reservoirs here, and you can see the reservoir up in here. And then let me show you this. This is the level indicator right up here. So we have one for the number 1 system, and then one, you can barely see it up in there, for the number 2 system. There's a bladder inside of this reservoir that has nitrogen in it that holds the pressure of the hydraulic fluid in the system. So this is a full closed loop system. We have 4 filters. We have a filter a return and a supply filter for each side. So we have 1, 2, and 3 of those. These are little pop-out indicators. If these were popped out, that would mean that our filter had bypassed. There's a 4th one on this side. So we have a set of servos on the bottom. These actuators are pitch, roll, and collective. So we have the cyclic pitch, the cyclic roll, and the collective pitch. Those are each of these 3 control rods. So these servos right here are actuators, are driving the system normally. If we have a failure, we have sensors that sit up in the very top up here that sense that if one of these actuators starts to fail, it has an auto switchover mechanism, which is this mechanism right here, and it will sense that and auto switch, and the pilot will not even know that the hydraulic system went from number 1 to number 2. The aircraft is unflyable without a hydraulic system. You can't move the flight controls, so if you lose both systems, it's not good. So we'll show you later in a video during the actual run-up, but we actually forced the system to the number 2 system, and we started in the number 2 system. We do a hydraulic check, and then I can watch annunciator lights, and I reset the system, and it switches it back to the number 1 system. This is to verify that both systems are active. If you were to just take off without doing this test, you would never really know whether the number 2 system worked until it switched over, which would be a bad time to find out that it didn't work. So to my knowledge, there hasn't been any of these systems have dual failures, but this is probably the most critical system in this aircraft. Because of the rigid rotor, the flight control loads are very, very high, and this is our biggest concern from a safety perspective. These support arms right here, there's 4 of them, those actually do the lifting. So if we look up on the rotor system on this side, these are the flight control rods that you saw down here. These are the high pressure, the high load side of the rods, and as they come up, they go into these mixing units. One of these is pitch, one is roll, and one is collectively moves the pitch of all the blades and moves the swash plate up and down. These are all cotter pinned. We're checking for the cotter pins here as we did before. This is a drive link. This drives the upper swash plate so that these PC links always stay perpendicular to the rotor system. The 2 support arms you saw down there meet up into here, and this is another titanium fitting that's on the rotor system that provides all the lift. So the lift for the whole helicopter is from those 4 support arms. Primary structure of the aircraft is aluminum. As you can see, the landing gear are quite beefy. 3 fuel tanks, has a main fuel tank and 2 header tanks. When we start the aircraft up, we started on the header tank, and then once the aircraft is running, we turn on the transfer pumps, and it's transferring fuel into the header tanks that are up under the floor right here that overflow back into the main tank, so it keeps positive pressure on the fuel system. So that's why we don't have we don't have any issues doing aerobatics, that we get air embolisms into the fuel system. Very critical for what we do. So as you saw some of the maneuvers here at our display, when I roll the helicopter, I'll pull the nose up. As I get the nose above the horizon, I'll start to roll the helicopter with the cyclic. At the same time as I'm rolling and getting through about 90 degrees of roll, I'll actually lower the collective. The collective pitch is over on the left side here, and I'll move this collective pitch down. As I move the collective pitch down, there's a lot of coupling between the flight controls. So when I move the collective up, the nose will want to pitch up and the helicopter will want to roll to the right. When I lower the collective, the nose of the helicopter will pitch down and roll to the left. So unlike an airplane, when you roll an airplane, you pull up and you roll the stick over. In the helicopter, we're using both cyclic and collective because we take that coupling to an advantage to help increase the roll rate. At the same time, because the nose is dropping, as I'm inverted, it's really raising the nose and allowing me to hold altitude in the roll. So I use a combination of flight controls to do these maneuvers. Unlike an airplane, we want to keep the G off of the helicopter because we have limits that are much less. In a normal airplane loop, you'll be between 3.5 and 4 Gs. In my loops, I can loop the helicopter as low as 1.8 by using down collective, forward cyclic to unload the rotor system to keep the G off of it. So when I'm coming out of a loop, unlike an airplane, as opposed to pulling aft cyclic or aft stick, I'm actually putting forward stick in and up collective. If you were to apply normal airplane aerobatic flight control inputs to a helicopter, it probably wouldn't end well. You would probably over-G the aircraft. So to go out and experiment with this on your own without having a good mentor would be impossible. Red Bull and myself are the only ones currently doing this. Red Bull, all the Red Bull pilots were taught by Rainer Wilke, a very well-known, accomplished, probably the most accomplished aerobatic helicopter pilot in the BO-105 from German Air Force. I was taught by Rich Lee. Rich was the former Hughes, McDonnell Douglas, and Boeing test pilot. If you saw an Apache do rolls and loops at Farnborough and at all the air shows around the world, it was probably Rich doing that. Fortunately, he lives in my hometown and has been my mentor since the early 90s and taught me to do aerobatics in the Notar helicopter and my Hughes 500C in the mid-90s. You need to have the aircraft, you need to have a mentor. That's why you don't see many helicopters doing what we do. You can go to pylonaviation.com, check out our website. We have a lot of information on there. We also have a YouTube channel, and you can find us on social media, Instagram and Facebook.